much for joining us here today at 9.connects. You're in for quite a treat here because you are here for our webinar on PCB board design to contain and control electromagnetic fields. And the great part about this is that it's going to be presented by PCB guru, Rick Hartley. So before we do begin, I just want to have one quick housekeeping note for you. If you have any questions for him, feel free to write those in the questions panel that is provided in your webinar. So when you basically logged in, you were able to get that panel. That panel is going to have a questions capability in there, so make sure that you write those in there. He's not going to be able to look at them while he's giving the presentation. However, he is going to answer some of those questions thereafter. And of course, we'll accumulate all the questions and answers and try to get a Q&A sheet out thereafter. So I don't want to hold us up any further because he's got a lot of great information. Let me just introduce our speaker here. This is Rick Hartley. He has served as a principal engineer at L3, I believe over 2 decades. And so he has a lot of experience in printed circuit board design. He's now the principal of our Hartley Enterprises, and he does consult internationally. So a lot of countries and a lot of companies that in those various countries contact him for a lot of issues that we deal with all the time: EMI, noise, signal integrity issues. The other thing that's really amazing about Rick is that he's been quite the pioneer in understanding high-speed design issues. As many of you may know, academia is not necessarily involved with those types of things, so it's really great that Rick not only has that practical experience, but he's been willing to share that with the rest of the industry. He is very active in both the IEEE and the IPC, and also has various leadership roles, I believe, in both organizations, especially the IPC. So if you ever go to any PCB conference that is out there, more than likely he'll be there and be more than happy to meet you. He's authored numerous technical papers, and he also instructs on a high-speed design course. It's a 2-day course, and I'll talk a little bit more about that at the end. So without a further ado, I'm going to turn the comm over to our friend here, Rick Hartley.
Thank you, Paul. Very appreciated. Anyway, to continue what Paul was saying, this presentation basically is less than an hour. It'll be just under an hour. We're going to, in effect, give you a small drink from a fire hose. There's a lot of information that can be talked about with regard to this topic. One of the first things I ask people who contact me and say, we've got an EMI problem, we have a noise problem, we have a this or that problem, one of the very first things I ask them is, what's your board stack up? Because I have found over the years that the thing that has the most impact on containing and controlling electric and magnetic fields, basically controlling and containing energy, is the board stack-up itself. And so we're going to talk a little bit about where energy travels in circuits, what impact that has on board stack-up. Then we're going to talk about a couple of board stack-ups in the time we have to give you an idea of exactly what we mean by this. Anyway, from the 1950s to the middle 1980s, basically PC boards could be laid out in any manner that we chose to do so. I mean, people did ridiculous things back then, and it truly was a connect the dots arrangement. As long as you had no shorts or opens, everything was going to work, and that's basically how it was. The reason is very simple. Frequencies back then were so low that every circuit on every circuit board was a lumped element. Circuits that we put on boards are basically a lumped element at low frequencies, and they're a distributed element at high frequencies. What does that mean? A distributed element is something that is sensitive to virtually any interaction from other circuits. Meaning it's long enough relative to frequency of what's in the circuit. It's long enough that you need to pay attention to its impedance. You need to usually terminate the transmission lines themselves. You need to be cognizant of things like crosstalk, power distribution. All of these things matter. And it's at distributed links that things become critical. They were lumped back in the day. They're now basically distributed. Thinking in terms of propagation time and rise time, or slew rate, however you choose to look at it, basically circuits are lumped if they have a long rise time compared to propagation time. So it's a function of how long is the line, not in terms of inches or millimeters, but in terms of how long it takes the energy to move down that line. Now, there is a direct relationship between the inches, the length in inches and millimeters versus the time, because energy in a circuit board travels at approximately, and don't use this number explicitly, but it's roughly half the speed of light. Energy in circuit boards moves at about half the speed of light, or about 5.9 to 6 inches per nanosecond, about 150 millimeters per nanosecond. So based on that rate of energy movement, if rise times are short compared to that, the energy coming down the line can rise all the way to its maximum level. And as it charges down the line, it runs into the high impedance at the load at the end of the line and causes reflections, and all sorts of things go wrong. So if a circuit has a long rise time relative to prop time, it's lumped. If it has a long propagation time relative to rise time, it's considered distributed. Very important thing to understand, it has nothing to do with the clock. The clock is completely irrelevant. You can be clocking at 1 cycle a day, and if you have rise times that are in the order of 300 to 400 picoseconds, and that line is longer than 1/2 of an inch, well, you're going to be in trouble if you do nothing about it. It just doesn't take a very long line with today's rise times to cause a problem. Something else to understand that is very important. Everything that goes wrong in a circuit, and I mean everything, all reflections, all crosstalk, all EMI, all power distribution problems, power bus noise, etc. All of these events occur during the rising and falling edge of the signal. Once a signal has gone high or gone back to its low state, nothing goes wrong. It is all about rise and fall time. It all comes down to exactly that. One of the things we need to understand when we're trying to contain and control fields is inductance. What causes inductance to be high or low? Let's examine that for a moment. Inductance is an impedance to change in current flow caused by the mass of the magnetic field. The mass of the magnetic field, I mean, how big can it be? Well, it's not large. It doesn't have a large mass, I should say. But the reality is when you have energy moving at half the speed of light in a circuit, it doesn't take a lot of mass to create a lot of inertia. And what we have to overcome in order to keep inductance low is to overcome that inertia. How do we do that? We do that by keeping the mass of the magnetic field as physically small as we're able to do. And the best way to do that, I was taught in college that the traces on the circuit board, if you make them wider, you'll lower inductance. And there's some amount of truth to that. There is a relationship between trace size and inductance. But the key thing that lowers inductance, the main feature that lowers inductance, is to keep the proximity between the trace and its return path as tight as reasonably possible. Now, obviously, there's a point where you can get the trace too close to the return plane. And when you do that, now you put yourself at risk of creating such a low impedance that it can cause other problems. But in fact, when we're talking about transmission lines, we want to control inductance. We want to keep it low. When it comes to power bus, when it comes to power delivery, we want the impedance of the power bus to be extremely low. And all of that requires low inductance. And the way, again, that you achieve low inductance is by tight proximity. If you have, for example, a pair of vias delivering power from a decoupling capacitor into the planes of the circuit board, how do you keep the inductance of those vias low? Is it by making the vias large? Well, the answer to that question is no. It's not about large vias. It's about having the forward via, the voltage via, and the return via, the ground via, have them be near one another, as close to each other within reason as good manufacturing rules allow. That's what minimizes inductance. It's about proximity. And the same thing's true for the capacitance of a transmission line. We keep capacitance high by creating tight spacing. When we do that, that gives us the ability to control impedance. But the main thing we want to focus on here is the size of the fields. And we can keep those fields contained by creating tight spacing between lines. So next question, what is energy? The basic answer from a physics book is it's the property of matter that manifests itself as the capacity to perform work. It's basically the motion or interaction of molecules. Energy comes in many forms, as everybody here knows. You can have mechanical energy, which is energy in motion usually. You have sound energy, you have light, you have electrical energy, heat, and so on. And some of these energy forms, energy is never lost or destroyed, as most of you know. it simply can be converted from one form to another. You can turn mechanical energy into electrical energy. You can turn electrical energy into motion. You can do any number of things. By the way, just as a case in point to make sure everyone is aware of this, the only difference, and I mean the only difference between electrical energy and light energy is frequency. Frequency. Light energy is a much higher frequency than electrical energy, but other than that, they are exactly the same thing. They are both waves made up of electromagnetic fields. That's exactly what both of them are. So where is energy in a circuit? Is it in the voltage or is it in the current? Well, the answer, unfortunately, is neither. The energy is in the fields, the electric and magnetic field, those things we've been talking about up to this point. And next question, where are the fields located in a circuit? Are they in the traces or are they in the planes? And the answer again is neither. The fields are in the dielectric space between the trace and plane. The fields are in the plastic and fiberglass of the circuit board. What I'm telling you is the energy is not in the copper. The energy is in the space between the copper features. The energy in a circuit is all in the fields, and the fields are all in the dielectric space between the copper features. And that's something that is really important to understand if you expect to control and contain fields, and most of all, keep fields from one circuit from interfering with fields of another circuit. The reason so many people have EMI problems is they don't understand this and they don't set up circuit boards correctly to accommodate. The energy, the E and H fields, in a transmission event is called a wave. It's an electromagnetic wave traveling down transmission lines. The traces, or the trace and plane that make up the transmission line, steer the energy from point A to point B. These copper elements act as a waveguide. A waveguide, oh yeah. Yeah, I've heard the RF engineers on our company talk about waveguides. RF circuits have waveguides. Yes, they do. So do all circuits. All traces routed relative to a return feature are a waveguide because all of them steer energy through the circuit board from point A to point B. What is this? It's a waveguide. This is a waveguide. If I apply an energy source, and you wouldn't do it as I've shown here, this is a drawing for the sake of discussion. If we were to apply an energy source to the middle points of this waveguide, this metal waveguide, and the half wavelength length of that energy was equal to the distance x from center to center on the sidewalls, we would get a true standing wave inside this tube, and the energy would move down the tube unabated from one end to the other. This is a waveguide. Well, wait a minute, Rick, you just said a trace and a return plane were a waveguide. They are. They're both waveguides. Here's an example. In this drawing, the element on the right-hand side is called a substrate integrated waveguide. The element on the left-hand side is called a microstrip transmission line. It's basically a trace routed relative to a plane. What happens when you establish a structure like this? The energy comes through the microstrip as it would with any circuit board where you have a trace routed above a plane. It comes through the dielectric between the trace and plane, and it enters into this substrate integrated waveguide. And as long as the frequency of it has a half wavelength equal to the halfway distance around this waveguide, you'll get a perfect standing wave, and the energy will move through the waveguide smoothly and unabated. Here's a picture of basically what the fields look like. You can see the fields have a little less control in the microstrip portion of the waveguide. There's a little bit better control in the substrate integrated waveguide portion, but the reality is both of these features are waveguides. One just controls the energy movement better than the other. By the way, just as a case in point, you see these vias that are spaced X distance apart? I've met many RF engineers in my life who believe you have to plate the edges of circuit boards to contain fields. bull. If that were the case, these vias, they're very close together. They're close enough together, they're a lumped length apart, which means they look like a wall of vias. They look like a solid feature, even though they're not. And the same thing is true with the edges of circuit boards. They do not need to be plated to contain the fields. This is a lot of RF engineers don't understand. So whenever we route a trace on some layer of a PC board, we are basically routing half of a transmission line, or half of a waveguide, however you choose to look at it. The return side of the transmission line is a return plane, or in some cases, a return trace. You can route two traces side by side. One of them can be the signal, and the other be we'll call it ground for the sake of discussion, can be the ground line or a return line. They can be side by side, which is called a coplanar waveguide. They can be one over the other, which is an adjacent layer waveguide, or they can be a trace relative to a plane. These are all features that are referred to by people in the know as waveguides. If we fail to fully understand how to set up the return side of the line, we'll create field spread, and we put our circuits in harm's way with regard to noise. In other words, if we don't set everything else up correctly, we won't properly contain fields, and if that happens, effectively, we are toast. So a transmission line is any pair of wires or conductors used to move energy from point A to point B. Move energy from point A to point B. If the IC on the left is point A, it's the driver driving this transmission line. As you can see, the copper features and the dielectric between them are made up of elements, and they show these elements in a transmission line as the resistor is the resistance of the copper. The inductor on both sides effectively is the inductance of the transmission line, based partially on trace size, but based mostly on spacing between them. The resistor going line to line is an attempt to show, when you're doing a transmission line model, is an attempt to show that the dielectric material itself is not perfect. It has some loss associated with it. In other words, there will be some amount of energy that is lost to the impedance of the material itself. Remember, the energy is moving through the plastic, not through the copper. It's attached to the copper, but it's moving through the plastic, and that's what that resistor is attempting to show. And of course, the capacitance is shown by the capacitor in this circuit. This is called a distributed model. The voltage is across the copper features, so from the line to what we'll call the ground line ground, or a plane. We'll assume for the moment it's a plane. The voltage is from the copper routed line to that plane, and the current is in both lines. Remember, the energy, the fields, are in the dielectric, and all the energy is in the field. So the energy is moving through the dielectric. I've heard many engineers in my career say, yeah, when you set up a transmission line like this, you shove current into the trace, and it goes down the line, is received at the load, and then the energy, the current, returns back to the source through the ground plane. That is not at all what happens. What happens is the fields leave the driver, move into this dielectric space that you're seeing, and as the fields move through the dielectric space, they create a current. They create a voltage across the two copper features simultaneously between the two, and they create current in both the forward and return path simultaneously. In other words, current, forward current and return current are established by the moving waves as the waves move through the transmission line. If we were to push a wave into this line and move it a third of the way down the line, at some point where it was at that space, at that point, there would be voltage across the first third of the transmission line, and there would be current in both halves of the transmission line, both the trace and the plane. The reality is, because the energy is only moved a third of the way down the line, there would be no energy in the back 2/3 of the line, there would be no voltage, and there would be no current because it hasn't gotten there yet. But that's in effect how transmission lines work. What you do with the return side of this line, OMG, does it matter? Can it be a power plane? Well, yeah, it can be if you set it up right. Meaning what? Meaning If it's a 3.3 volt signal, it better reference a 3.3 volt plane. Because if you reference a 3.3 volt signal to a 5 volt plane or a 2.5 volt plane, how's the return current going to get back to the driver as it's coming back through the plane, which is not attached to the driver? It's highly likely that a 5 volt plane won't be attached anywhere to a 3 volt driver. So how's the energy get back? It doesn't. It doesn't have a path. And this creates discontinuities that cause field spread and can lead to serious EMI problems. It won't create a signal integrity problem because the energy will find a path back. It's just that the path it finds will be ugly and you won't like it. And it'll create noise, and it probably won't create enough noise to cause a signal integrity problem. But I can tell you from past experience, it will create more than enough energy spread to cause EMI problems. So be careful. So what can it be? It should be, as often as possible, a ground plane. And it has to be properly placed on the board as well. And we're going to talk about that as we go. Let's take for an example for a minute, a 2-layer circuit board. Looking at it from the side, you have layer 1 with routed signals. And let's imagine, if we will, that this is an RF board. This is a 1 or 2 gigahertz RF board. So it'll have routed power, and it'll have poured ground copper on the remainder of the top side of the board. So layer 2 will be a solid ground plane. This is pretty typical of how microstrip type RF boards are set up. Layer 2 is ground. Layer 1 is some ground, routed power, routed signals. By the way, I hope all of you are aware that when you're dealing with analog circuits, you do not need a power plane. Power for all analog circuits, regardless of frequency, can be routed because the way power is taken into the IC to drive analog signals uses a filter that's designed to resonate at the frequency of the device. And you don't need power planes to distribute power on the analog side of the board. Just make you aware of that. Now, if we take this circuit board and rotate it so we're looking down on the top, we can see the ground plane on layer 2. This is a drawing, of course, but we're trying to illustrate an idea. Ground plane on layer 2. We have a trace routed on layer 1. We have a trace routed on layer 1. We have a couple of ICs. There's many ICs on this board. Imagine that. These 2 ICs happen to be sitting at the top and bottom on the right-hand side. They're attached to the ground plane where the X's are on both ICs. And you have a trace going around the perimeter of the board. When I start working for the first time with an engineer whom I've never worked with in the past, whether it's on a consulting basis or when I was still working in industry, if I moved companies, one of the first questions I would ask them is, where's the return current flow in a circuit board of this type? And the answer I get from 80% or more of the engineers I ask is the energy, the return current, will take the short straight path from 1x on that, from one of the attachments of the IC to the plane, the shortest path it can take across the plane to the other IC. If this were a DC signal, pure DC, without even an AC component in the current, both current and voltage were AC or DC, that would be the case. The current would take the short path, but it would also take all the other paths across that plane. In other words, at DC, the entire plane would get used as a return path. As you go up in frequency, by the time you get to a few hundred cycles, a few hundred hertz, the energy would start to focus itself in one place on the plane, one place and one place only. And by the time you are above a kilohertz, and certainly by the time you're out of the audio range, all 100% of the return current will be directly under the trace back to the driver. If that distance between those 2 X's across the plane was 1 inch and the distance around that trace was 20 inches, the current will take the 20-inch path and will ignore the 1-inch path at frequencies above a few hundred hertz. The reason is that's the path of lowest impedance, the path of lowest inductance, and the path of greatest capacitive coupling. And that is the path the current will always take in a situation of this type. And basically these arrows are showing, the arrow pointing to the left is showing the forward current, the arrow pointing to the right is showing the current in the return plane directly underneath it. And the energy would just move around the trace from one side to the other. The return current would stay under the trace in all cases. 4 circuit boards. This is a picture from Professor Wu from the National Taiwan University. 4 circuit boards. The one on the left, the bit large gray area, is a plane on layer 2. The crosshatched line is a signal on layer 1. So you have 4 different arrangements. You have one with a solid ground, you have one with a split ground, and you have 2 of them with crosshatched ground planes. Except that case 3 has the trace routed above a section that isn't crosshatched, easy for me to say. Case 4 shows the trace routed above the openings in the plane. The question Dr. Wu asked when he presented this at the IEEE EMC symposium, which of these will have the best EMI signature, meaning the lowest amount of radiated energy, and which of these will be worse? And the room had about 100 people in it when he asked the question. About 80 of them, about 80% of the room said case 4 will be the worst. Let's examine that. Based on what we just said a moment ago, I think since you know that the return current will stay directly under the trace, I think it's safe to assume, and I'm sure all of you get this, that case 1 and case 3 are going to be almost identical. Here's case 1 and case 3, and they have almost identical EMI signatures. Case 4 is the crosshatch plane, case 2 is the split plane. Here's case 4 in gray, and look at case 2 in purple. It's 20 to 30 dB worse than cases 1 or 3, depending on the frequency where we're looking at. 20 to 30 dB worse. Why? Let's look at current patterns. Here's the return current patterns in the plane. Case 1 and case 3. Again, case 3, even though it's a crosshatched plane, has a solid section of plane under the trace. So the majority of the return current is contained where it should be, hence the EMI signature shown here. Look at case 4. You get a little bit of field spread. You would expect that. You're routing across the openings in the plane. Some of the fields are going to spread out, and they're going to create current in a wider swath, and that's going to create what we see in gray. Look at case 2. OMG. This is ridiculous. Rule number 1 in circuit board design: you never, ever, 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 ever route across a split ground plane, period. Now, the truth is, rule number 1 should be don't split ground in the first place. There's almost never a reason to split ground, even though every app note on the planet says, oh yeah, you've got to split ground between analog and digital, or you have to split ground between RF and what. No, you don't. That's what they want you to believe, but it's wrong. But if you are going to split the plane, you cannot do this. Bad plan. What about a 2-layer board? If we have routed traces on both sides of the board without a plane anywhere other than poured copper on the surface layers, what's going to happen here? Well, obviously, this looks like the same thing we just looked at. We're routing multiple signals across splits in the layer below. This is a bad plan. What I haven't shown you thus far in this picture is that some of these traces, all the ones highlighted in white, are ground traces. My friend Dan Beeker, who works for, I forget the name of the company, they used to be Freescale Semiconductor. Someday we're all going to work for the company because everybody's buying everybody else. Oh, it's Qualcomm. That's who he works for now. He designed this board working with one of his customers who needed a 2-layer design to get rid of an EMI problem the customer had created in their initial design. And what he did was route, and I'm going to move to the next slide, which shows just the top layer of the board. He had the customer, or it is people, one of the two, reroute this so that every pair of signals had a ground line routed between them. My friend Dan refers to these as triplets. A triplet. There's one set of triplets, then a second and a third, and so on. And each of the pairs of signals have a ground line routed between them. What does that do? It helps contain the fields and keep them from coupling through the splits on the split openings on the layer below to keep fields from spreading. Is this an ideal way to do this? No, it is not ideal. If you're ever going to put a guard trace in a circuit, this is far from an ideal guard trace, but it is better than doing nothing. People who do nothing really put themselves in harm's way, and this is much better than doing nothing. Notice the ground, the solid ground under the IC. Why did they do that? Because this IC doesn't have enough ground pins to truly be designed as it should. We're going to talk about that in just a moment. To truly be designed as it should be designed. And so Dan had them put a ground plane underneath it and attached all the grounds to that to help lower the pin inductance of the IC to help contain fields from the IC to keep it from becoming part of the problem. So they use that for that purpose. Here's the bottom side of the board where we're showing triplets also going off, in this case, in the X direction. Same exact design. Notice too that on this, they have routed power. That wider trace is routed power. If you're going to route power, you better know what you're doing. You better do it properly. And oh, by the way, they didn't do this properly. If you go to PCB West or go to any of the conferences where people who are in the know talk about these things, you'll find out why. So what's wrong with this board stack up? Well, basically, it's a 4-layer board with signals on layer 1 traveling in the X direction, in other words, across the screen. There are signals on layer 2 traveling into and out of the screen in the Y direction, and there's a ground on 3 and signals on 4. I think the signals on 4 are safe. They're not going to create a problem. But what's wrong with the signals on 1 and 2? Well, when you try to move energy through them, the fields from layer 1 are going to couple to layer 3. The fields from layer 2 are going to couple to layer 3. And in that dielectric space between layer 2 and layer 3, those fields are going to intermingle and couple to one another. We're only going to create millivolts of interference here doing this because these are routed in orthogonal directions. It's not like there's going to be a massive amount of energy exchange, but there will be energy exchange between the fields. And it's going to be a few millivolts, not enough at all in a digital circuit to even remotely cause a signal integrity problem. If all you care about is signal integrity, you'll never see a board like this. But if you care about EMI, this board is a serious problem, and you absolutely don't want to do this. So what's the solution to this? Route layer 1 in triplets. Now you have a return path that's coplanar to the signals to help contain the fields to keep most of the field energy from layer 1 from wanting to couple to layer 3. Easy solution. Here's a circuit, an analog circuit. This is an amplifier. This is the output shown when it's functioning as everything should function. There's a second circuit on this particular circuit board that was sampling an accelerometer. When that accelerometer was being sampled, and only when it was being sampled, this output that you see here went to this. Not exactly a good thing. The accelerometer sampling circuit, when it was in use, was interfering with the amplifier's output, causing this ridiculous modulation of signals from one circuit to the other. How did this happen? Well, for one thing, they used the circuit board on the previous page. Signal, signal, ground, signal. Bad idea. The solution to fix this, I'm not even sure that triplets could have solved this problem because this is a sensitive analog circuit. The solution in this particular case was to go to a 6-layer stack-up, which I'm going to talk about in a short while and explain to you why it helped. ICs. What about ICs? Do these ICs, containing fields in ICs is also extremely important. How do you do that? Well, by creating low inductance pins. Well, how do you create low inductance pins? By having a lot of power and ground pins intermingled with the signal pins. Do either of these ICs have that arrangement? No. Believe it or not, as bad as the IC on the left is, it's actually better than the BGA on the right. Most people I know think, oh, BGAs, they're fantastic. Low inductance. Yeah, that BGA on the right is awful. You couldn't get much worse than that because there's almost no place for any of those signals to couple to power or ground to have return currents going back into the IC to return to their source. These signal pins are going to use each other as a return path. It's as simple as that. These are a perfect example of extremely poor IC design. Here's something that's considerably better. You can see there are many more powers and grounds in this particular package that's shown here. This is an Altera Stratix 2 FPGA. It's better than the previous ones. However, there are still regions in this part where there are not adequate powers and grounds, not adequate returns, meaning that these signals are going to use each other as a return path. They're not going to return in power or ground. They're going to use each other as a return path. Here's an IC that's better than the one on the right. It's considerably better. Why? Because there are many more powers and grounds. And if you look carefully, you'll notice that virtually every signal pin is one pin's distance away from power or ground or both. Every signal pin, the little X's, are one pin's distance away from power or ground or both. The IC on the right, though better than the ones on the previous slide, are still, this IC on the right is far from perfect. In fact, so much so that it caused 5 times greater cross-coupling between signals than the IC on the left. This was a study done about 12 to 14 years ago by the ever-present and always wonderful Dr. Howard Johnson. He did this study called BGA crosstalk. Why do you think he called it that? Because these pins are cross-coupling to one another, using each other as a return, because there are not adequate ground pins and power pins in the package. Design of the IC is just as critical as design of the circuit board. What about connectors? How does this look? Well, you've got 93 million signals in the middle of this connector, 4 grounds on one end, 2 powers on the other. Oh, yay, what a great idea. You know how many times in my career, 53 years I worked in industry, I've seen this done by people who didn't have a clue? This is a terrible idea. All those signals in the middle are going to use each other as a return path. The only time power will return in ground is when it's truly pure DC and there's no AC element at all in the current. That's the only time power will return in ground. None of those signals will ever return in the power pins or the ground pins except for the signals right next to power and ground. This is the same number of pins with power and ground redistributed. And what does this do? Well, it helps control and contain fields. And it gives every signal pin a ground pin or a power pin to use as a return path to get from board to board. This is a much better design, same number of pins. If you can afford to increase pin count, then this is better still, because now every signal pin is referencing both power and ground. And even better still is this arrangement, where we have a seesaw mechanism of the signals and a seesaw mechanism of power and ground. Why does that help? Because we're reversing fields from one side to the other, which is like putting 2 magnets side by side. If you put the north poles next to each other, they're going to repel each other. If you put the north pole next to the south pole, they're going to attract each other, and that's going to cause the magnetic fields to contract. This bottom structure is the best of the 4 shown here. Whenever you're assigning signals to connectors, think about this. So, board stack-ups. What's wrong with this particular board stack-up? This is a 4-layer board. This is a 4-layer board that everybody in the world uses. Power on 2, ground on 3. What's wrong with it? Just about everything. Most severe problems this has are power delivery, very poor power delivery. Why? Because this is a 1.6 millimeter thick board, which means the spacing between, because of the way boards are fabricated, and I hope all of you know this, the spacing between power and ground will be about a millimeter, be between 35 and 40 mils, just about a millimeter. And because of that wide spacing, you're going to have high inductance and high impedance of the power bus, which means the planes are going to do very little to almost nothing to help deliver power properly to ICs. Secondly, how do you change layers with this board? If you have a signal on 1 that has to go to 4, where are the fields going to be with that layer 1 signal? Well, they're going to be in the dielectric space between layer 1 and 2. A lot of people say, oh, it's going to be in the copper on layer 1. No, it's not. It's going to be in the dielectric space between 1 and 2. If you're going to change layers with that, you have to move that set of fields down to the dielectric space between 3 and 4. If power and ground are in the middle of the board, how are you going to move those fields? Well, the answer most people give is the energy will move through the decoupling cap. And if your circuit board, if you're lucky enough to have rise times that are in the 2, 3, 4, 5 nanosecond range, yes, you can get away with this. If you're dealing with the kind of circuit boards that most people today have, where rise times are in the order of 300 to 700 picoseconds, this circuit board isn't going to get the job done because the decoupling caps are going to run out of gas. And once they do, there's not going to be any place with a low impedance to move those high frequency fields from one dielectric space to the other. This is a bad board stack. So what is the solution to this problem? If you want to have a board stack that doesn't have the problems we just talked about here, what's the solution? Fairly simple. Here's two board stacks that completely solve the problem. Let's take the one on the left, for example. The first time I ever had to do this, I was working at Goodrich Aerospace. It was 1995. We had a 4-layer circuit board that was in a product. It was a very low-cost product. It was designed purely for commercial aviation, for the weekend pilots who fly around and need low-cost equipment in their aircraft. And we designed this system that had one circuit board in it. And this one circuit board was a 4-layer to help keep costs down because we were selling this dirt cheap. We had an EMI problem. And the original board was this board stack up right here. This is the board stack up we originally designed. We moved to the board on the left here because by doing so, when we moved all the signals to the inner layers, several things happened. One, we got better containment of the signal fields because now they were strip line instead of microstrip. They were all referencing the grounds that were poured on layers 1 and layer 4. The signals, because they're not trying to fight for space among the components, there was a ton of open space now on the signal layers because those pesky components weren't in the way, which left enough space for us to pour copper on all the open areas between signals on layers 2 and 3 and attach that to power. You don't need full power planes in a circuit board. You need power structures that create low inductance, because to achieve low impedance at high frequencies in a circuit, it isn't about how much capacitance is in the planes. It's about how low the inductance of those planes are. When you have the planes on layers 2 and 3, the inductance is pitifully high. When you move the power to pores, as shown here, to partial planes on the signal layers, where they're close to the ground on the top layer and close to the ground on the bottom layer, now we have a low inductance structure. And the same thing is true of the one on the right. The only problem with the board on the right, because we're putting signals and poured power on the same layer as the ICs and the other components, if the board is very dense at all, you're going to have a heck of a hard time designing a circuit board. If you have high density, you're probably going to want to go with the stack up on the left. Ever since 1995, we used the stack up to solve our problem. We got a 14 or 15 dB improvement in the EMI signature of our circuit simply by going to this board stack up. Ever since 1995, every 4-layer board I've ever designed has looked like one of these two. Here is what the planes of a conventional 4-layer board with power and ground on 2 and 3 look like. This is what the impedance of the planes look like. Going to this one of these boards here, the plane impedance improves to what you see in red. That's a 5x improvement. That's a 500% reduction in power bus impedance, simply by going to partial pores that are very close to the ground. Why does that reduce impedance? Because it drastically reduces inductance, and to some degree it increases capacitance. And that drastically lowers power bus impedance, which lowers switching noise and gets rid of countless problems. The other advantage, going back to this for a moment, that these boards have, when you change layers, every signal is referencing ground. All you have to do is drop a ground via near the signal vias, and now you have a path to carry the fields from the dielectric space on 1 and 2 down to the dielectric space between 3 and 4. Very simple, very elegant, easy to work with. Here's a 6-layer board that is an endless problem for most people. Everybody on planet Earth that I know of uses this 6-layer board. What's wrong with it? Well, where does power come from in this board? If I walked up to most engineers, most EEs, and said, where does power come from in this board? They would, with great pride, say, oh, the power plane on layer 2. Incorrect answer. The power from this board comes from the dielectric space between layer 2 and layer 5. There's this huge dielectric space that's even bigger than a conventional 4-layer board that has very low impedance. It has high inductance and low capacitance. It has very high impedance, because it's such a wide space. The energy for power delivery comes from that large dielectric space. Well, what else is occupying that large dielectric space? All the signals on 3 and 4. Their fields are also in that same dielectric space. So what's going to happen? Every time you deliver power, you're going to interfere with the signals on 3 and 4. Every time a signal line, a transmission line, is driven by an IC on layer 3 or 4, it's going to interfere with the fields in the power bus. And these fields are going to intermingle, and they're going to get together, and they're going to party. And it's not going to be good for the people trying to make this thing work properly. From a signal integrity standpoint, again, this won't create enough of a problem to cause an issue. If all you care about is signal integrity, hey, knock yourself out. This board will be just fine. But if you care about EMI, or if you're doing analog design where you care about even a small amount of interference, this is a very bad board stack up. What's the solution? The solution is to keep the same board stack, except put copper pores on all 4 signal layers, attach the copper pore on layers 1 and 3 to the ground plane with lots of vias. How many vias? A via every 20th wavelength of the maximum rise time frequency. Ooh, what does that mean? If rise time is 500 picoseconds, what's its frequency? It's roughly a gigahertz. Come to a class at PCB West, you'll learn why. It's roughly a gigahertz. What's the 20th wavelength of a gigahertz? It's about 0.6 of an inch, or about 15 millimeters. Wow, you mean we only have to have vias every 0.6 of an inch? That's correct. Or maybe a little tighter. And you can make them tighter if you want. They don't have to be, but they could be. That's assuming a rise time is 500 picoseconds. If it's half that, if it's 250, well, then you got to place the vias half that distance apart. Anyway, you get the point. So ground vias from the ground pores to the ground plane, and on the other signal layers, we're pouring power, and we're going to attach those to the power planes with power vias, layer to layer to layer, and so on. Why does this improve things? Where does power come from in the board on the right? Power comes from the dielectric space between 1 and 2, and the dielectric space between 2 and 3, and the dielectric space between 3 and 4, and 4 and 5, and 5 and 6. Power doesn't come from one large high impedance dielectric space. It comes from a bunch of small low impedance dielectric features, all of which have tight containment of fields, all of which work well with one another. The other thing about this that's good, all of the signals now are referencing the plane directly above or below because of the way the copper pores occur. So the signals, instead of intermingling with power, are next to the power instead of being coupled with power. They're side by side, so you're not worried about the fields from the signals coupling into the power. Now, you're still going to get some field coupling. It's not, with a board like this, you're not going to completely eliminate it. With low layer count boards, there's no such thing as perfect. But this is infinitely better than the board on the left-hand side of this picture. What do the power planes look like? Here is the set of power planes from the board on the left. If we look at the board on the right, because we have multiple power features, all of which have low impedance, the planes look like this. This is a 10x improvement. This is an order of magnitude lower impedance than the circuit board without the copper pores. Very plain, very simple. I don't care how you do it, you have to contain and control fields. One last slide. Here is a recommendation of a major IC company. I'm not going to say their name, but this is a large IC company, one of the largest on the planet. I think you get the picture. In their app note, with their almost 1,300 pin high-speed microprocessor, they recommended this for people who must have a low layer count board. They said the best we were able to do was an 8-layer board that looked like this, and we were able to get it to work in our lab just fine. I can believe with enough on-die and on-package capacitance that they were able to make this thing work, because the power delivery is far less than ideal here. But if they put enough capacitance in the package, I can imagine they got this thing to function and have good signal integrity. What I can't believe and won't believe is that they did any EMI testing. There is not a chance in Hades that this board could pass EMI testing. Look at power plane 1. Where are the fields going to couple from power plane 1? In other words, where's the return current from power plane 1 going to be? Well, most of it's going to be in power plane 2. It's not going to be in the ground on layer 2. It's going to be in power plane 2, which means the majority of the fields are going to couple down to the plane below. What's the power plane 2 going to do? Couple to the plane above. Those fields are going to intermingle with each other, and oh my God, is it going to be bad. Now, somebody said to me once, yeah, this is an 8-layer board, Rick. You can make that core really thick. Yeah, that's a good idea. Then you solve the problem. No, you don't. If you make the core thick, you get power 1 and power 2 away from each other. But now look what happens. Now power 1 will return in the ground plane. Guess what else is in that same dielectric space? A bunch of signals. Anytime you put a signal or a set of signals between power and ground, you're begging Mother Nature to do you harm. Think about all this. I hope there was some value in this for each of you. Thank you very much.
Well, we're coming towards the end of our hour over here. Just want to thank you, Rick, very much for taking the opportunity to present here today. For those who are out there, you are here today for a reason, because number one is Rick Hartley, but also an opportunity to get another perspective on the high-speed design issues. So, well, who are we? We here at 9.Connect's PCB organization. What do? We do sell software products specific to PCB design. We also have services as well. But more importantly, and that's why we brought Rick here today, is to also show you that we're very interested in the education of the industry in regards to PCB design. We do that in various different ways. We do it through webinars, we do it through short videos, blogs, and we do it through articles. And of course, if you're looking with something, because a lot of times we just simply put those things out there for your consumption, but if you are looking for something in which we actually work with you for a couple of days or through several coaching sessions, we do have what we call our training and our coaching. If you're interested in any of the information that we've shown here today, feel free to take a look at our website at www.9.connects.com. So I know we're here at the end of the hour. I want to thank you very, very much for attending, and we look forward to seeing you at our next webinar in August. Take care and have a great day.